fibers locally are all equivalent, then they are equivalent with the...
Yes, but think of, for example, I mean, there's a
the
method
limits.
called the limits, yes. Okay? Okay, and then there is strongly rigid, which obviously is the strongest notion. So if I take the set of all y which are homotopically equivalent to x, they consist of a finite set of isomorphism classes of globally rigid varieties. Okay?
So do you assume here that y is of the same dimension as x?
Yes,
If it's homotopically equivalent,
Yeah.
yes.
I mean, I forgot about compactness.
Yeah. Okay, and then we have another notion we call X étale rigid if every finite unramified cover of X is rigid. So this you can apply to rigid, we would call it étale globally rigid if every finite unramified.
Whole combinations.
Huh?
Whole combinations.
Yes. Okay, so just a remark about this: infinitesimally rigid implies locally rigid, and that's because H1 of theta is just the Zariski tangent space of the Kuranishi space. So this is the germ of the semi-universal definition of X. So this means that def X consists of a reduced point if H1 of theta is 0. Strong rigidity, of course, implies, just by definition, global rigidity, and global rigidity implies local rigidity. Of course, étale rigidity implies rigidity, but the converse in general is not true. So there are rigid varieties which have unramified cover.
So which rigidity do you mean?
Sorry?
When there is no adverb. Adjective, thank you, sorry. To your rigidity, so which one do you mean?
Local.
The one
Local.
which is, well, I mean, I explained it. So every unramified covering
okay.
is
You see the
rigid. So
brackets.
yeah, here I mean local, but you can also do it. Étale global rigidity implies global rigidity. Okay? So if the base of the deformation of the map is reduced by the Grauer-Fischer theorem, local rigidity yields triviality of the family over a suitable neighborhood of B0. So the family is really a product locally. This is not true in general if B is not reduced. And I mean, as you know, this Kuranishi space can be, it's an analytic space, but it can be non-reduced. And then M of X, I define the dimension of the Kuranishi space. And it's the number called the number of moduli, and this is bigger or equal by Kuranishi's theorem, the dimension of H1 of theta minus H2 of theta. Okay?
So that's dimension around x.
Yeah, and this is the germ. Okay? Okay, so the first trivial remark is that if the dimension of X is 1, all notions of rigidity coincide, and the only rigid curve is P1. Okay? If X is a smooth, compact, complex surface, then we can rewrite the inequality I gave before. So this is the so-called Kuranishian recursive inequality. So the dimension of the semi-universal deformation of S is bigger or equal H1 minus H2, and this is by Riemann-Roch minus, this is minus chi of theta S plus H0, and then by Riemann-Roch this is just 10 times chi of OS minus 2k squared plus H0. Okay? And here is the first proposition. If X is rigid, and here rigid is locally rigid, then the Kuranishi space def X has dimension 0. So this is clear by Grauer-Fischer if it's reduced, otherwise you have to use a small argument. And in particular, if X is a smooth, compact, complex surface, and the right-hand side here of this inequality is bigger than 0, then S cannot be rigid. So this gives numerical restrictions on when a surface can be rigid. Okay? Now, this is a theorem which is rather surprising. What are the rigid surfaces? What happens in dimension 2? So if you have a smooth, compact, complex surface which is rigid, then either S is a minimal surface of general type, or you have very few possibilities. S is a Del Pezzo surface of degree bigger or equal to 5, or it is an Inoue surface, so it's a non-algebraic surface, and there are 3 types. So Inoue surfaces, they are characterized by having first Betti number equal to 1, second Betti number equal to 0, and no curves. And there are 3 types.
Kato surfaces are also rigid.
But there are curves. No curves. No
No,
curves.
they have
They have curves, yes, but just as no, have no curves.
Yeah. But the force, that's the force.
I don't think so, but I mean,
Okay.
What is
Kato
the question?
surfaces. I think this is probably a part of.
Cutter surfaces which are obtained from
Excuse me?
germs. Cutter surfaces which are type 7 zero surfaces.
But they
That
are,
would be 2 is bigger than 0.
yeah, but
No,
there
they're
are
not.
curves.
But
No,
if
they're
B2
not.
is bigger,
They're not rigid
rigid.
because
if
it's
B2 is
must
bigger
have
than-
B2 equals 0.
Yeah.
From the theorem before.
From the
That was
inequality, you see minus k squared. So chi is equal to 0 and minus k squared is B2.
It's positive.
So if this is positive, they cannot be rigid.
They are deformed to hope, you're right.
Exactly.
Blown up.
Okay?
Yeah.
Sorry, I would help us if you blow up
Do
points
we
of not in general
enlarge?
position.
We need
Yeah,
to
sorry.
deform.
They just told me
If you blow
this
up
is
points
what
not in general position on P2.
Yes. I mean, then you can deform them,
In the general.
right?
Then you can deform the general.
Okay? You just move them out and they have deformations.
3 points on lines.
Yeah? Okay. Yeah, and then you move the point out and you get the different. Okay? So, so there are just very few possibilities. In particular, either the Kodaira dimension is minus infinity or 2, and the Kodaira dimension 0 and 1, they are not there. So, let me make just a few remarks. So rigid surfaces of general type, they're also globally rigid. They're locally rigid implies globally rigid because you have a moduli space, right? The surfaces, the Inoue surfaces, which I mentioned, they are infinitesimally and globally rigid. The Del Pezzo surfaces of degree bigger or equal to 5 are infinitesimally rigid, but the only one which is globally rigid is P2. Okay? So that's your example. You can move 3 points in general positions to 3 points on a line. So in the limit, they are not rigid. We expect that there are rigid surfaces of general type which are not infinitesimally rigid, but there are no examples yet. So one would somehow try to have a surface which has a -2 curve, a rigid surface of general type which has a -2 curve, then h1 of theta is bigger than 0.
So what you part 1, so is it a converse? Is there a converse to this thing? Or are there minimal surfaces which are or general type which are non-rigid?
Which are not rigid, there are.
Of course.
Also,
But your converse is, yeah.
No, yeah. But you see, the point is infinitesimally rigid implies rigid.
Yes?
But rigid does not imply infinitesimally rigid,
Right.
a priori. Okay?
And by infinitesimal rigid, you mean h1 of theta is it?
This is infinitesimally rigid. By rigid, I mean just any deformation in some neighborhood is isomorphic. Okay? So let me give a sketch of proof. So the main point, so let me for the moment assume that S is algebraic. Okay? But this is anyhow, the first steps are valid anyway. So assume S is rigid and not minimal. Then you blow down -1 curves until you arrive at the minimal surface S prime. So at each step you have a 1-point blow up here. Okay, and then there is a result by Kodaira which says if Si is rigid, then Si plus the pair Si plus 1, Pi plus 1 is also rigid. But I can move the point. So this means if I move the point, I get isomorphic surfaces. So at each step I have a 2-parameter family of automorphisms. So this means that the dimension of out S prime, which is Sk, is bigger or equal to 2k. In particular, there are 2 linearly independent global holomorphic vector fields. And then I get an exact sequence where D1 and D2 are bigger or equal to 0, are effective divisors which go to theta S prime, and the co-kernel is a coherent sheaf which has support of dimension at most 1. And then I take the determinant of this exact sequence and I see that minus ks prime is bigger or equal to d1 plus d2. And this means either s prime is root or ks prime is trivial, and then s prime is a torus, but they are not rigid. Okay? So then you go on, s prime is either a 2 or is a p1 bundle over a curve of genus, a curve C of genus G, and it's easy to see that this curve C is P1, so it has to have genus equal to 1. And then you see, if you, for S, we have this inequality, 10 times chi minus 2k squared is less or equal to 0, you immediately see that ks squared is bigger or equal to 5. Okay? So this inequality, if you remember, this is a lower bound for the dimension of the deformation space, and the deformation space has to be 0-dimensional for rigid. And then it remains to exclude the minimal surfaces of Katsudai dimension 0 and 1, and the non-algebraic surfaces. Okay? Now, you see, if you have rigid varieties, how can you construct? So I'm just trying to explain you now why in higher dimension we don't expect this exceptionality. Either you have Kodaira dimension 2, or you have just Kodaira dimension minus infinity.
So probably it would just take product.
That's what that's what I'm trying to say. So suppose x and y are infinitesimally rigid, then x times y is infinitesimally rigid if and only if. That's Kunet's formula essentially. If h0 of theta x times h1 of oy, and just the same with the roles of x and y interchanged if this is 0. Okay? And then also if I have an étale map, so a finite unramified covering, if C is rigid, also X is rigid, or if C is infinitesimally rigid, X is
I
infinitesimally
think
rigid.
you mixed up delta x here, or so something.
No, it's theta X and OY, and
But
here I
each 0
have...
x is usually 0.
Yeah, but it's not say that they're of general type. This is more...
Ah.
If they're of general type, there is no condition.
No
Yeah.
condition. Ah, okay.
Okay?
Ah, okay.
Yeah. Okay, so as I said, in 2, the converse does not hold. There are counterexamples which I explain later, the so-called Pouville surfaces. They are étale quotients of a product of 2 curves. They are rigid, but the product of 2 curves is not. Okay, so what happens if you are in higher dimension? What Kodaira dimensions for rigid manifolds do you have? So for a curve, you only have minus infinity, so 0 and 1 is out. For surfaces, we have minus infinity and of general type. So is this phenomenon that 0 and 1 is missing, is this general? So there is an easy example. So you take the Fermat elliptic curve, x to the 3 plus y to the 3 plus c to the 3 is equal to 0, and here you have a standard action of c mod 3 squared. So you take a third root of unity and you multiply with the first generator of G, you multiply x with epsilon, and here you do it on the second factor. And then if for n bigger or equal to 4, there is a free G action on an n-fold product of E. You just take this action and on each factor you twist, and then you look that there are no common stabilizers. So for n bigger or equal to 4, you can obtain this, and then x, you take the quotient by G, then this is a complex manifold. It's smooth because G acts freely, and it's infinitesimally rigid. For this, you just use again Kühne formula, and there are some, because you see you don't have that h0 of theta of the components here vanishes. You have some condition. So for n bigger or equal to 3, we can construct with essentially the same construction, that just that we replace some of the elliptic curves, we replace by a certain curve of higher genus, which has not a G action, but the action of a finite 3 group of order 3 to the 5, which has seg mod 3 squared as a Boolean quotient. So you can construct rigid manifolds of dimension n and of Kodaira dimension between 2 and n. Okay, so here we don't have dimension n equal to 3, but you can do exactly the same thing here with 3. Then you get a singular Calabi-Yau, which is rigid, which was already constructed by Deauville, I think, in the beginning of 80s or something. Okay, so what is easily done is to construct for n bigger or equal to 3, Kodaira dimension 0. I mean, minus infinity is still there is always Pn. Kodaira dimension 0, and everything between Kodaira dimension 2 and n. Kodaira dimension 1, we didn't succeed with this construction, but we strongly suspect maybe one has to go higher, a little bit higher with n, and also Kodaira dimension 1 should be there.
If you have hyperclavier with bit equal 3, then it's twistor space is rigid dimension 1.
I'm sorry, I
There is
didn't.
no such thing.
No, but there could be quotients.
Could be.
Yeah.
Quotients by final groups, like in the first case.
Ah, I see.
Okay, so now I would like to come back to rigid surfaces of general type. So there is a list of the known examples, which is strangely enough not so long. So there are of course ball quotients. So these are smooth projective surfaces whose universal covering is the two-dimensional complex ball. And by results of Moscow and Seo, they are pluririgid. I just wrote briefly pluririgid, which means strongly rigid, infinitesimally rigid, and étale rigid, so in all possible senses. Then there are somehow the analog, the irreducible by this quotient. So the universal covering is a product of two one-dimensional disks, and irreducible means that the two projections of the fundamental group to PSN to R has dense image. And by results of Yost and Yao, they are also strongly rigid. They are rigid in any possible sense.
So this includes Bagit surfaces, right?
No. These are the next ones. You see, the difference is that you don't have this intermediate. Here in between you have a product of two curves. Yeah? It means just it acts reducible, so it factors through a product of two curves. So Bouville surfaces are rigid surfaces of the form S equal to C1 times C2 mod G. G is a finite group acting freely. And you can describe them completely algebraically. There are many examples known. So essentially, if C1 is different from C2, then it's just given by G acts on Ci, on C1 and on C2, and C1 mod G is isomorphic to the projective line and it ramifies in 3 points. Okay? So they are infinitesimally and strongly rigid, but obviously not entirely rigid. Okay? So that's also a difference to this case here.
And how does one prove strong rigidity here?
How does one prove strong rigidity? That's essentially, I mean, that's a result of Fabrizio in general on this surface is isogenous to a product. So you essentially show that a surface with the same fundamental group and the same, I don't know, k-squared, maybe k-squared, even though the Euler number is already of this type. So, right? So this is a more general result. Right?
But in the second, do we have many examples? I mean, how we obtain that?
Yes, so there's somehow, actually there is a long list by, they're related to quaternion algebras.
They're all informed by orders.
Yes, exactly. And there is, I mean, there are many examples. There is even, it seems that there is a classification now, for example, for the smallest possible Euler number, so for k squared equal to 8. K equal to 0. But there are many examples. And then there are Mostosio surfaces. They are ramified coverings of, they are not ball quotients, but they are ramified coverings of ball quotients, and they were constructed by Mosto and Sio, and they show that they have a strongly negative metric, right? And that's why they are also pluri-rigid.
What is ramification? Can you remind? So most of it's ramified covering.
Yes, but
What kind of?
I don't know. I think it's smooth disjoint curves, but I'm not sure. I mean, I don't remember the construct.
These are covering of the ball.
Yes.
Yeah,
There's some ball portion,
Yeah.
and then you ramify over certain geodesic curves,
yeah.
but which don't intersect.
Right.
So more than one component.
Yes.
Yeah,
It's more than
so
one
it's,
component.
it's quite difficult to structure by most.
It's not, it's, could you mention 2 separators of curves? I mean,
No.
could you mention 2
Ah,
real
The universal cover is a branch cover of the ball, branched on geodesic curves.
Yes.
Codimension 2, yes.
mhm.
Real codimension 2.
Okay. So, and they are also rigid in any.
And they, are there algebraic models around?
Are there?
Are there explicit algebraic models like
No.
Covering, what else?
coverings of what?
Ball portion.
I mean, most of just construct the groups by
Yes.
reflections.
Yeah.
Yeah. So what do you mean by explicit? So they give
Yeah.
a group of
equations.
No.
That's what
Yeah.
we're trying to do.
And then there are some Kodaira fibrations. Actually, I think they're double Kodaira fibrations, which were constructed by Fabrizio and Sönke Rolenske. And they are strongly rigid, but I don't know about infinitesimally rigidity and vital rigidity. And then there are the so-called Hirzebruch. That's what we did in this paper, the Hirzebruch-Kummer covering of exponent n bigger equal to 4 branched on a complete quadrangle. So I will talk about this in a minute.
So it's not hypercadar.
No, Hirzebruch-Kummer. I'm sorry. So there is just one thing which I would like to observe and which probably Fabrizio will talk much more about it. So a compact complex manifold is called projective classifying space if its universal covering x tilde is contractible. And it's a very strange fact, which we cannot explain, that all known examples of globally rigid surfaces except T2, and for 6 we don't know, but for all the previously known, there are projective classifying spaces.
But they're not projective we see projective, but it's not projective manifold. Right? Not all.
Genotype.
Compact convex manifold is called projective manifold.
If it is
No, it's
projective,
Right,
right.
it is projective.
Always?
No,
No,
also
no, no,
In
it's
these
not-
examples, it is general type, yeah?
Yeah, for surfaces.
No, no, no.
The word projective is missing in this definition.
I think it's called a projective specified space if it is projective.
Yes.
and
I see.
I'm
universal
sorry.
Because
type.
for examples with Rollensky, I think of this type, right?
Yeah, they are
This
not.
double codera, they are this type and not projective.
Alright, they're not projective.
Yes. No, you're right. I should have written here, but I mean, yes. Here I'm talking about surfaces of general type. I should have added projective and universal covering. Okay, but anyhow, all known examples of globally rigid surfaces have contractible universal covering. And the question is this just a coincidence? Up to now, there are no counterexamples. So, now, anyhow, there are many open questions here, and I think Fabrizio will come back to this. What I want to talk about is now is this Hirzebruch-Kummer coverings branched on line configurations. So, what is this? So, you have a number of lines, L1, Lk in P2. And then you also add the points P1, Pn of multiplicity at least 3. So these are the points where at least 3 lines pass. So as the master example here, somehow we take the complete quadrangle. So this means we take 4 points and all lines. So we have 6 lines. So here k is equal to 6, and then we have 4 points. Okay? So, and these points, they have multiplicity, they are triple points, yeah? 3 lines are passing. And then we take the following construction. You just embed P2 by these linear forms in Pk minus 1. And then you take the nth root here. So you map C to C1 to the n up to Ck to the n. And then you take the fiber product X. Of course, this is singular if you have multiple points. So in our case, this will be singular over the points P1, P2, P3, P4, and then you take a minimal desingularization of these points. And this factorizes, you can also blow up here P1 up to Pn and call this P2 hat. And then this map here is a Galois covering with group C mod n to the k minus 1. So k is the number of lines. Okay?
And what is the branch divisor? Just the one and
So the branch divisor is just the lines and then the exceptional curves over the points. Okay?
So it has k plus n components.
Yes. It has k plus n components. That's right. So they were these Hirzebruch-Kummer coverings. They were very extensively studied by Hirzebruch. And then there is this book by, I think it's the PhD thesis of Thomas Höfer, and then there's a book by Barthes, Höfer, and Hirzebruch-Höfer, because they wanted to construct ball quotients. As Sasha asked, is there an algebraic model? It's very difficult to give an algebraic construction of ball quotients, and they are difficult to construct, so they just try to see whether they can construct ball quotients as Kummer coverings of the projective plane branched on line arrangements, because a ball quotient is just detected by the turn numbers. Okay, and this, if you have these Hirzebruch-Kummer coverings, you can calculate all turn numbers of this surface S. Unfortunately, they didn't find much, so Hirzebruch showed that S is a ball quotient for n equal to 5, and the configuration is the complete quadrangle. That's the one I just was drawing over there.
I'm sorry, what is n? I forgot.
N is the exponent. If I take the nth root, yeah? Take the nth root of the lines. So the dual Hesse configuration, and if n is equal to 3, the Hesse configuration. So what is the Hesse configuration? So if you take a smooth cubic in P2, a smooth plane cubic, and then you have the 9 flex points. These are the points P1 to Pm. And then if you take 2 flex points in the line joining them, then there is a third one. So that's the Hesse configuration. It has 9 points. So n is 9 and k is 12. And the dual is just to exchange the role of points and lines. So there's not really very much. And so Hirzebruch showed in the case, for example, the complete quadrangle for n equal to 5, if you take the set mod 5 to the 6 covering, then you get a ball quotient, and S is rigid, of course, and the question is, what about the other n? They are not ball quotients, but still they could be rigid, and that's our main result. The Hirzebruch-Kummer covering, let me just for a moment call it Sn, phi from Sn of exponent n branched on a complete quadrangle is infinitesimally rigid whenever n is bigger or equal to 4. So for n equal to 2, it's a K3 surface, and for n equal to 3, we can show that H1 is different from 0, it's not infinitesimally rigid, and Rouleau showed that S3 is not rigid by showing that there is an impal quotient which moves. Okay? So let me give an idea of proof, which is actually, I mean, you really have to get your hands dirty, which I will not show, but let me just give a rough idea. So you have to blow up P2 in these 4 points, P1, P2, P3, P4, and this is the del Pezzo surface of degree 5, and this is now a Galois covering with group Z mod n to the 5, so number of lines minus 1, and it branches on the strict transforms of the 6 lines here plus the 4 exceptional lines over the points P1 to P4, and this means it branches on the 10 lines on the del Pezzo surface of degree 10. So let me just for the moment, this is the union of D is the union of 10 lines. And then I write D sigma is the component of D having sigma as local monodromy. Sigma is an element of Z mod n to the 5. And then I take OS, the holomorphic functions, and I take the direct image, and then I split it in character sheaves L psi. It writes as a direct sum L psi to the minus 1, where psi goes over all the characters. And then there is a formula essentially by Rita Pardini, which reads in our case as follows. The ith cohomology group of theta with character minus psi, that's equal to H2 minus I, because we prefer to work with differential forms. So it's omega 1 y log with logarithmic poles along those d sigma such that psi of sigma is different from minus 1, and then you twist it by ky plus L psi. Okay, so it is clear it's everything down on the del Pezzo surface. And this for each character, and this means if I want to prove that H1 of theta s is 0.
And I'm sorry, L psi is some explicit line boundary, yeah?
Yes. Yeah. So, I mean, if you have a covering, you have this L psi given. If you have the L psi given, you have the covering. But in our case, we can calculate them explicitly. We are on the del Pezzo surface. So this means we have to calculate this h1 of omega 1y with these logarithmic poles twisted by ky plus m psi for each psi. So first of all, I mean there are many. Z mod 5 to the 5, that's already a lot. And actually I would like to do it for more general coverings. So one would like to try somehow to systematically do it. Eventually I would like to use a computer. So how to calculate all this? So first of all I would like to prove a result for all n. Right? So now what have to do? First of all we have to classify all possibilities for this ky plus m psi. And psi, of course, depends how many psis I have, depends on n, but the possibilities of all these should not depend on n. And then I would like to have some kind of general vanishing theorem for twisted logarithmic differential forms.
Sorry, I was just going to ask you, I mean, doesn't logarithmic Nakano or Kazuki or something like this?
No.
So there is nothing ample inside that you have?
No.
Ah, okay.
So the first one is done by the following lemma. So for psi, for any character, so we write L psi as a divisor, and you write it in the standard generators of the Picard group of the Del Pezzo. So L is the transform of a line, the pullback of a line in P2, and E1, E2, E3, 4 are the exceptional curves over P1, P4. Okay? And then the coefficient here can only be between 0 and 5. And the lambda i's are between 0 and 2. And these numbers 5 and 2, they are not just by chance. In general, this is bounded by the number of lines minus 1. And this is bounded by the multiplicity of pi minus 1. So this does definitely not depend on n. This we can do for any configuration.
So now for lines where you have monotony about.
Yes, I mean you just I start with a line
Or
arrangement.
yes,
So
and then
I
you have
start
cyclic.
huh? Yeah.
And then you have characters, so
Yeah.
no
Okay. So I start with I mean I can take any configuration, just a number k lines.
Yes,
Okay?
yes, yes,
And then this is bounded by k minus 1.
ah,
Okay? Now, it's the general vanishing theorem, and that's actually rather technical. So, suppose Y is a smooth projective surface, and then you have smooth rational curves on them such that, so they have global normal crossings, D1 is the n. And then I have a certain number, I mean, okay, so I'm interested in this one, okay? So let me just explain you how you divide them. So I have, can I erase this or? Just because it's very ugly. So I have D1 and then d mu and then dl plus 1 dl plus 1 dr plus dk. So these are the numbers mu, l, r, k. So this one is A. B. Sorry, this one is B. So this will be the negative part of the twisting. Okay? Then A, it starts from here and goes to here. So A and B are disjoint.
So your blackboard it starts with n plus 1. Yeah?
Yeah, you're correct. Okay? And then dk, I have to go on, I mixed up, yeah, okay, no, I'm sorry, I'm very sorry.
A is actually
so basically you
No, wait, so this one up to dk
is A.
is A, and the logarithmic part is here. So this is the logarithm.
So, I don't understand. Is there something between mu and L?
Maybe. Not necessarily. Could be also mu equal to L. The only thing which I need is that B and A is disjoint, which I can always arrange somehow, right? Sorry? And what I'm saying is that B appears, the negative part appears in the log part,
Yes.
and A can have a log part and more.
Ah.
Okay? So then this vanishes, provided that
Sorry, can I just ask you, what is this notation with the 1 log d1 log dr?
it's just, you can also write log d1 plus
Plus
di
di,
because it's normal crossings, it's the same.
No, but I mean,
And do you have some assumption on the
it's
group
generated by the logarithmic derivatives of those.
Yeah.
of each-
So I mean d1 plus dr, that's the...
Huh?
I mean, sorry, the usual notation, how I know, I mean, it's log...
Yeah. In that case, it's
No,
the
but
same.
that's for normal crossing.
Mhm.
You see, if you have a conic
Yes?
which specializes to the union of two lines,
Yeah.
you can just take the logarithm of xy,
Yes?
dxy divided by xy.
Okay.
You're not adding dx over x and dy over y, so it's different.
Yeah.
In your case, not.
Yeah,
Yeah.
good.
In our case, there's no
Because there's
difference. I mean, because in Pardini's formulas, you don't need this log d1 plus, they are different logs. But in this case, it's just the same. Okay, so now, so this is 0 provided that. So first of all, H2 has to vanish. In our case, this is no condition at all because this is a summand in H0 of theta S, which is 0 because S is of general type. So this is always satisfied. And then we have intersection conditions. That's maybe your question, right? di times A minus B has to be bigger or equal to -1 for all these. And here I just wrote stars. I have other explicit intersection conditions.
How many?
Hmm?
How many?
Another one.
Ah, just one.
Which are, I mean, here there are more di's involved. That's not a big problem. Okay? The really serious problem is this one. So what is this? In a certain sense, so I have to intersect with the negative part. Okay? And which one do I have to intersect? Essentially all of A. All components of A. I have to intersect with the part B, and the rank should be bigger or equal to the rank of the Picard group minus mu, and mu is the number of components of B.
What do you mean by the rank?
The rank of the Picard group.
Because it's big. Why is covered?
The rank of the subgroup generated by this di?
Is
No.
the rank of the DIs.
Of the eyes is Picard generated by this? Picard of Y.
The
Of
rank of a set is the number of maximum number of linearly independent elements.
Yeah, no. But Picard is Picard. Y is covered, yes?
Yes. No, Y is not covering. Y is the del pezzo surface.
Yeah, outer.
So, of course, the del pezzo surface is generated by all the DIs.
So if you have an inequality, then you actually have an equality.
Right. You have actually an equality. Yeah? So, but this is rather tedious. And let me just say why. So, in a certain sense, we have, here it's just very innocently written log d1, log dr. So what are these d1, dr? These are just those of the 10 lines where psi of sigma is different to -1. So you can work, to show that, so let me just write, because this is really complicated, and it depends also, A minus B is K plus Ly. So this d1, dr in our case it's nothing else than the d sigma with psi of sigma is different to -1. Already classifying when it occurs that this has not rank 5, what you expect, is rather, you really have to work on the del pezzo surface and on the symmetries. That's rather a nice thing, but what we really need is a classification when the rank of this, and then I put that it's orthogonal to certain other divisors, and it has not the expected rank. So it's like a more delicate question there. Anyhow, for the complete quadrilateral, or the del pezzo of degree 5, we can verify for almost all cases this condition. And you see, this I can implement in a computer, except that I cannot make the computer choose a decomposition which is satisfying these things. So sometimes it happens that you can decompose k plus l psi in different ways, and one works this theorem and the others not. Okay? So there we are really, so I'm just working now with Roberto Pignatelli on the Hesse configuration to try to implement this, that many cases are ruled out by this general vanishing theorem, and still we have a lot of trouble. So let me just make a remark. So this can be carried out in the case of the complete quadrilateral by hand. It's not very nice, but still. This implies, of course, that all étale quotients of Sn are infinitesimally rigid. And that's where the story started, because for a special n, for those co-prime to 6, there is a quotient which is a set mod n squared covering branched on this complete quadrilateral which were constructed by Catanese and Wettweiler to give a negative answer to a question by Fujita. And that's where the story somehow started, that we started to prove that these are rigid. Then we thought if we can prove that the Kuma covering is rigid, then it will be implied, and so on. So the questions which just for this special configuration remains open is whether these Hirzebruch-Kuma coverings of exponent n are projective classifying spaces. And we don't know whether they are strongly rigid. So there are partial answers to this, because if n is equal to, if n is divided by 5, then there are ramified coverings of all quotients, and then there is a paper by Fanyang Zheng who extended these methods of Mostow and Seo to normal crossing branching, as if you have branched coverings of all quotients branching on normal crossing, not on smooth divisors. So for these, he can construct a metric of negative curvature, and then by the Cartan-Hadamard theorem, the universal covering is contractible. So strongly rigid also we cannot prove, it's the question whether it is. And then actually it's a conjecture that these Hirzebruch-Kuma coverings should be rigid if the exponent is big enough for many other configurations. Right? The dual Hesse configuration, the Hesse configuration. Then we have another configuration we would like to test, and that's somehow it starts, you can iterate here. So if let me just draw these lines, how they are. You see, then you add this triangle here. This means you add 3 points and 3 lines. And then, of course, you can iterate this
Yeah, keep going, yeah.
as many times as you want.
Mhm.
And you get a series of line arrangements where you could test whether you can calculate the h1 of theta, or you find another method to prove rigidity. Okay, so I think I stop here. I just mentioned very few questions, and there are a lot of open questions they came up when we started to study rigid varieties of manifolds, so we continue on this.
Other questions, comments?
So you don't know whether for some angles these varieties are not projected. So there is a non-trivial homology.
There is a non-trivial?
There is a homological sphere, yes. So sphere which is realized in some sense.
Homotopy, you mean? Homotopy.
Homological sphere,
No.
non-trivial homology.
Well, actually, this is somehow difficult. I think that for n at least 5,
Yeah.
so we believe that they are projected classified
Yeah.
space. I gave a criterion but couldn't find the proof.
Mhm.
Also, Panov, he used some idea of Kontsevich and Gromov.
Yeah.
Maybe, I don't know whether this is in the next of your transparency.
No. I mean, he's claiming, he's
Panov
constructing this
claims
cut
that
zero
for n
matrix.
large enough,
Yeah.
they are projected classifying spaces, because you can construct like a polyhedral
Yeah.
Yeah.
metric of negative curvature. But it's the way it's written, it's totally, I don't really understand. And in fact, he thinks that there is another method to prove that it's for n at least 5.
So he was claiming it for n very large. I mean, I tried to read the paper. At a certain moment, there is in a crucial point inequality in the wrong direction, and I thought, well, it's a misprint. But then he uses it in the wrong direction, so I don't know. I cannot understand the proof. But I think we believe that in this case, it's well.
Yeah, but there's no better proofs.
Yeah, hopefully.
Yeah, but it's a standard trick, triangulation, basically.
Yeah.
You can make triangulation, which has kind of too many triangles around the vertex. That's a standard. So you can see by local triangulation.
Yeah.
Sometimes
Yeah.
it is
Well,
it's something negative curvature everywhere. Negative curvature. Okay.
Questions?
Questions will go to both.
Okay. Thank you very much.
Thank you.
The next in half an hour, and I suppose there was tea. I don't know, but Sasha.
Since I'm gone, I will explain other ideas for the proof, but they don't really want it. So it's the same with the Spanish method, and I have another criterion for what is the
I should tell you about
The problem with Pano is that it doesn't replicate, so at some moment you have to sit down. For instance, for any port 4, it is not. For any port 4, probably the turning point is 5.
I mean, the universal number
Means that you can do anything.
is very